This is our quadcopter height control final project. I'm Oliver Heatwell.
I'm Alcides Cordero.
And I'm Harry Booth.
Current regulations mandate that quadcopters must be flown a set distance above people in a populated area. However, quadcopters are notoriously hard to control with manual inputs. To increase the precision of quadcopters, it is necessary to implement a control system that takes into account many inputs to determine the desired output. By incorporating the height of the quadcopter into the control system, it is possible to use outputs as inputs, allowing the copter to regulate its elevation and adjust accordingly. With this control system in place, the height can be adjusted precisely and effectively to ensure the flight stays within regulations.
Our system input will be the desired height, powering the rotors to control the force they exert and therefore the elevation. Along with this input, there is a loop relating elevation changes based on these inputs to regulate the speed at which the elevation will change. The direct output of our system will be the elevation of the copter. We have included a gain K in our system to allow the system to become stable within the closed loop. H of T is the outputted elevation, Fr of T is the force of the lift, and Fg of T is the force of gravity. Average weights of quadcopters usually range between 1 and 3 kilograms. Also, dampening usually comes in at below a value of 1 for a quadcopter-sized vehicle. Because of these two known factors, we have set the quadcopter's mass to be 2 kilograms and the dampening to be 0. The dampening ratio being at 0.8, closer to the maximum for a quadcopter, will allow the stability of the height to be regulated efficiently. To analyze our system, we began with a root locus plot. This shows how the open loop system will respond as the frequency shifts. The location of the 0 in this plot will not allow the percent overshoot to go above 8%. After using Cisco tool, our open loop system, we found that the phase margin to be about 65 degrees and the gain margin to be infinite. This is due to the phase of the open loop system never reaching a value of negative 180 degrees. The stability of the system is bibow stable due to the fact that our poles are all in the left half plane and the plant is proper, having 1 0 and 2 poles.
Our designed closed loop system can be seen here. In our design, we set the percent overshoot to be 10% of our intended height. The reason for setting it to 10% was to reduce the amount of oscillation below our intended height. The goal of our control system was to reach a height and not go below, since that may cause many issues. To achieve our intended values, we modified the initial closed loop system. In this closed loop system, our disturbance was gravity, which can be seen entering the system after the gain. In order to overcome this disturbance, our gain was set to 19.62, which was derived from multiplying gravity by the mass of the copter. For this system, our mass was 2 kilograms, since that seemed to be the average weight of the quadcopters we researched. The reason we set the gain to 19.62 was to allow us to offset the disturbance caused by gravity and have our input values be relevant to gravity. During our design, we realized that entering a force and having the feedback return a height was counterintuitive, since this could not relate to each other. To overcome this issue, we implemented an input system that would take a designated height rather than a force. This height would then be implemented into a function that compared the intended height with the current height, resulting in a fraction. This fraction would then be multiplied by the gain. Setting our system up like this allows our force input to be related to the gravitational force. Simplifying our input to be related to the gravity helps our system stabilize much quicker than merely inputting a force that has no relevance to gravity or the height of the system. As a result, when our system approaches the intended height, our forces cancel out, leaving the quadcopter hovering at the inputted height.
The closed loop transfer function is defined by this equation here. The equation is obtained by closing the feedback loop, ignoring the negative input caused by the force of gravity applied to our system. and subtracting the value of the closed-loop system, ignoring the positive input given to the system. The value of k is the gain of our system, while m will be the weight or mass of our quadcopter.
The block diagram that was just shown in the previous slide was used in the simulated analysis of the closed-loop system. As you can see from the graph shown, the overshoot stays below 10% at multiple desired heights at both 25 meters and 50 meters. The rise time is also visible in these graphs, and it is obvious that it is different for the two heights. This is to be expected as it takes longer to reach larger heights. This displays how our rise time is a factor of our desired height. And it comes out to be about 3 seconds for every 25 meters increase in rise time. The stability of the closed loop system can also be seen by the fact that the graph levels out at our desired height. With these results, it can be clearly seen that our closed loop system does indeed meet our design specifications.
A system like this needs to receive feedback relatively quickly to properly adjust the height of the quadcopter, especially with how quickly a quadcopter can change height. Implementing a time delay into our system caused massive fluctuations in the response time of the copter and greatly affected the percent overshoot of the system. Seen here are the two systems with different height inputs and different time delays. For the 25-meter input, the allowable time delay was only 1/10 of a second, whereas the 50-meter input could accept a delay of 4/10 of a second. The reason the 50-meter height change was able to have a higher time delay was because the height change was greater. By changing the height by larger amounts, the copter essentially has more time to receive inputs. Therefore, feedback can be spaced out in larger increments while still falling within the 10% overshoot.
Some improvements that we would like to include in a future design iteration would be creating a more complex system so that we can regulate more variables besides height of the copter. And we would like to create a more intuitive design for the regulation of our height. That being said, we are very satisfied with the fact that we were able to reach a wide range of heights accurately and that our design met our specifications for overshoot and stability.